And let me make sure recording's working. Yep. Okay, and this covers derivatives as rates of change. Okay, so far we've been dealing with mainly just functions. So let's say we have some function f of t. Okay, so all this does is represent the position at some value t. And usually t is time, but not always. So an object's position at time t. And t doesn't have to be time. It could just be the variable that was chosen. But in most cases, they use t for time. Okay, so let's say, just to kind of visualize it, we have some random function. And instead of x, let's use t just to get used to the idea. And your y, remember, that's just your f of x, or in this case, f of t. Okay, so let's say that when t is equal to 1, your f of t is equal to 2. When t is equal to 2, let's put 2 right there, that could be equal to 2.5 or something like that, whatever the case may be. And when t is equal to 3, so if it's right there, then f of t is equal to, let's say, 3. Okay, so because all it does is show you where on the graph that value appears, that's why it's just called your position function. Okay. Now, in most cases, rates of change are measured in pretty much notation that you see every day and don't think about it. Measured in, say, miles per hour. That's a rate of change. Meters per second. And et cetera, and so on. Let me make that a little smaller. Okay. Now, the rate of change at some particular time So let's say the rate of change at the position function at the time that we will call t. That's just your first derivative. Which in some cases, I won't even say a lot, but some cases, they'll denote your first derivative as v of t, or your velocity function. And I say sometimes because every once in a while they'll try to be tricky. And instead of saying v of t is your velocity function, they'll say f of t is your velocity function. So they will try and trip you up a little bit. Now, the thing about velocity function is that it has directional components. And again, you see it all the time and don't even think about it. As directional components. And in some cases, they will actually list the directional component. Let's say you'll see like 10 miles per hour northeast. Which is not the same as 10 miles per hour southwest. Even though it's the same 10 miles per hour. Okay. Whereas your position function, whether you're facing north, east, west, or south, it's still that same position. It's no change to it at all as far as directional components. Now, when you couldn't care less about the direction and all you're worried about is the speed, then you're just looking for the absolute value of the velocity function. Okay, so when direction is not important, then the absolute value of the velocity will give us, make sure I have enough room. Move that over just a little bit. So the absolute value of your velocity function. And remember, that's the same thing as the absolute value of your first derivative. They're the exact same thing. So really, it's just a matter of notation preference. Both of those we call our speed function. And we'll finish up on the next page. Anyone still writing? Nope. All right. Okay, so let's say you wanted to measure the rate of change of your velocity. Now, again, you see that every day and don't even think about it. Because if you go from driving 60 miles per hour to 70 miles per hour, that's the rate of change of your velocity. In this case, it's just acceleration. So acceleration is the rate of change of an object's velocity over a time that we will denote by t. Okay. Now, since we already know that the first derivative, which we sometimes denote as v of t, that's our velocity function. So that means the rate of change of your velocity is measured in the derivative of your first derivative. That's the second derivative of t. Which is also the first derivative of v of t. So in most cases, I don't want to say most, in some cases, or a lot of the cases, you'll see that denoted as a of t. And I should have given that a little more room. I don't know why I made it so close. And this is called your acceleration function. All right. So any questions on that so far? All right. All right. Anyone still writing? All right. So let's say, for example, that a ball is tossed into the air. The height above ground is represented by the position function P of t is equal to negative 4.9 t squared plus 6t plus 2. Okay, so we want to know what is the rate of acceleration at t equals 0 seconds. Excuse me. Okay, so since we're looking for the acceleration at 0 seconds, remember your acceleration function is also your second derivative of your position function. So we know that P of t is equal to negative 4.9 t squared plus 6t plus 2. That's just your position function. So if we take the derivative of that, that gives us our velocity function, which is negative 4.9 times the derivative of t squared, which is 2t, plus 6 times the derivative of t, which is 1, plus the derivative of a constant is 0, so that just disappears. So I'll just put plus 0. You don't have to. So that means v of t is equal to, go ahead and multiply those two together, negative 9.8 t plus 6. We multiply those two. Remember, this is your velocity function. Okay. Now, if we find the second derivative of our position function, that's just the first derivative of our velocity function, which will give us our acceleration function, which is what we're looking for. Okay. So really all we have to do is take the derivative of our velocity, which is negative 9.8, times the derivative of t, which is just 1, plus the derivative of 6 is 0. We didn't have to write it, but we did. That means our velocity function is just negative 9.8. Oh, forgot to put my a of t. I meant to put a of t is equal to v prime of t. There we go. Oh. Acceleration function. There we go. Okay. Now, it's completely common for an acceleration function to be a constant. So we know at t equals 0, the acceleration at t equals 0 is still negative 9.8 meters per second. Because there's no t to replace. All right. Any questions on that one? All right. Okay. Oops, still right. Okay. So let's say, for example, that a ball is dropped from a height of 64 feet. Its height above ground and that's in feet, is given by the position function P of t is equal to negative 16 t squared plus 64. Where we know that t represents the number of seconds. Okay. So first, we want to find the velocity and acceleration functions. And next, we want to know what is the instantaneous velocity when the ball hits the ground. Okay, so we already know that P of t equals negative 16 t squared plus 64. That's our position function. Now we know the first derivative, which is, let me make that negative a little clearer. There we go. So you have negative 16 times the derivative of t squared. So we bring down the 2. So negative 16 times 2 is negative 32 times t to the power of 2 minus 1. So that's t to the first power. plus the derivative of 64 is 0, since the derivative of a constant is always 0. So we know that v of t is equal to negative 32t. And we know that's our velocity function. And we just take the derivative of that velocity function, which is the second derivative of our position function. That's negative 32 times the derivative of t with respect to t is just 1. That's just negative 32. So your acceleration function is just negative 32. Like I said, it's pretty common for the acceleration function to just be a constant. Not all the time, but very common. Okay. Now for B, let me put A here. We want to know the instantaneous velocity when the ball hits the ground. Okay. Well, first we have to find out when the ball hits the ground. We know that when the ball hits the ground, that just means the height is 0. Okay. So since the height is represented by P of t equals negative 16 squared, negative 16t squared plus 64, that means the ball hits the ground when that height, P of t, is equal to 0. Well, the position is 0. So that means when negative 16t squared plus 64 equals 0, the ball is on the ground. So if we add 16t squared to both sides, we get 64 equals 16t squared, or 16t squared equals 64. So if we divide both sides by 16, that gives us t squared is equal to 64 divided by 16, which is 4. So if we square root both sides by the square root property, we see that t is equal to positive or negative the square root of 4, which is 2. Well, positive or negative 2. Now, t equals negative 2 really isn't valid since dropping the ball is at t equals 0. So we're not going in the negative direction. So we're just looking at t equals 2. So we know it hits the ground at t equals 2 seconds. So that answers the question of when it hits the ground, but we want to know what the velocity is when it hits the ground. Well, since we know that it hits the ground at 2 seconds, all we have to do to find the velocity when it hits the ground is just plug that into our velocity function. So v of 2 is equal to, our velocity function is negative 32t. That's negative 32 times 2. Which equals negative 64 feet per second. All right, any questions on that one? All right. Now remember, at the very beginning, we discussed how velocity can involve speed and direction. Okay. So let's say, for example, if we consider a particle moving along a number line. And that particle could be anything. Okay, let's say it started right here. Since it can involve directions, let's say if we're looking at it and it goes to the right, we'll call that positive direction. It's going to the left, that's our negative direction. Okay, so our positive velocity, we're going to denote that by the particle moving to the right. And our negative velocity, we're going to denote that by the particle moving to the left. All right, anyone still writing? Okay. So let's say, for example, the position of a particle moving along a coordinated axis is given by P of t equals t to the third power minus 9t squared plus 24t plus 4. And we're going to assume that t is greater than or equal to 0. Okay, so the first thing we want to do is we want to find the velocity function. Next, we want to find out when is the particle at rest. And then we want to find out on what intervals is the particle moving left to right and right to left. And the last thing we want to do is we want to sketch the path. So sketch the path of the particle along the coordinated axis. Okay. Well, for A, we know that our velocity function is just the first derivative. So the derivative of t to the third power, bring down the 3, times t to the power of 3 minus 1, which is 3t squared, minus 9 times the derivative of t squared. Derivative of t squared, we bring down the 2. So negative 9 times 2 is negative 18, times t to the power of 2 minus 1, which is just 1. So we can leave it as negative 18t. Plus 24 times the derivative of t, which is just 1. So 24 times 1 is 24. And the derivative of 4 is 0, since the derivative of a constant is always 0. So we know that our velocity function is 3t squared minus 18t plus 24. So for B, when is the particle at rest? The easiest way I found to approach them is to apply these to things you already know. You know that if you're driving your car, you're going 55 miles per hour, or whatever the case may be, then that's your velocity. Now, if your car is at rest, then you're going 0 miles per hour. So that means when you see something as far as like particle at rest, or something kind of close to it, that's just another way of saying your velocity is equal to 0. Or you could just say that v of t is equal to 0. And let me kind of separate that. And that was just a little note. So that means we want to find out when our velocity, which is 3t squared minus 18t plus 24, is equal to 0. Okay. Now we could factor this using the a times c method or the quadratic formula, but it'll be a lot easier just to divide each term by 3. So that would give us t squared minus 6t plus 8 is equal to 0. So if we factor that left side, that gives us t minus 4 times t minus 2 is equal to 0. So that means t minus 4 can equal 0, or t minus 2 can equal 0. Would make that true. Add 4 to both sides. So that means t can equal 4, or t can equal 2. Okay, so we know that the particle will be at rest at t equals 2 seconds and 4 seconds. And t equals 4 seconds. All right, anyone still writing? All right. Okay, so for C, we want to know when the particle is moving left to right and right to left. What intervals? Okay, so we know that if it's moving left to right, you remember, let me go back, I think second page, yep. If it's going in the left to right direction, it's moving in the positive direction. That means our velocity is positive, greater than 0. And it's moving from right to left. That means our velocity is less than 0. Now remember, we already figured out that our velocity is at rest when t equals 2 and t equals 4 from the previous page. So what we're going to do is take old reliable number line. It goes from negative infinity to infinity. And we know the values where it equals, where your velocity is 0. That's at 2 and 4. So let's say we'll let our t equals 2. Let me make that a little longer, just to ensure we have enough room to work. And t equals 4. Okay, and we'll draw a little dashed horizontal line to kind of let us know that those values are off limits, because we're not looking for equal to, just greater than, less than. Also remember that t is greater than or equal to 0. So we're just looking from 0 on forward. So that means everything over here we can kind of ignore. We don't even need that, at least in this case. So since t is greater than or equal to 0, that means we have the left bracket from the interval from 0 to 2. And t can't equal 2, so we'll put a parenthesis there. And here we have the interval from 2 to 4 seconds. So that's from 2 to 4. And here we have the interval from 4 seconds to infinity. And we put infinity because it just says t is greater than or equal to 0. It doesn't really give a time limit. Okay. So to find out, bring that down, yep, where the velocity is positive or negative, we want to plug in test values in each interval. So we're going to plug test values. Into the velocity function. Oops. And you could leave the velocity function as 3t squared minus 18t plus 24, but it'll be a little bit easier to factor it and plug in values in that. I mean, you could still plug it in here and get the same answer, but it'll just be a little bit easier to factor it. And really all it would be is 3 times all of that, but still the same values. So velocity function is going to be t minus 4, t minus 2. Let me double check. Yep. T minus 4 times t minus, make that a little bit wider. T minus 2. I swear every day I say I'm going to go home and get a new eraser, and I never do. This thing is down to nothing. Okay, so for the interval from 0 to 2, we can just plug in t equals 1. And again, that's completely random. You can pick any number between 0 and 2, except actually 2. Okay, so that means our velocity at 1 second is going to be 1 minus 4 times 1 minus 2. So our velocity at 1 second is going to be negative 3 times negative 1. So our velocity at 1 second is just equal to 3. So we don't really care about the actual value. We just want to know whether it's positive or negative. So for this interval, our velocity is greater than 0, so we know it's going left to right. Okay, now we do the same thing for the interval from 2 to 4. And again, you just pick any test value between there. I'll pick t equals 3 seconds. And again, that's completely random. Pick whichever number you like. You can pick 2.5 if you want to. That's perfectly okay. I just try to go with the easiest. Okay, so our velocity at 3 seconds is going to be 3 minus 4 times 3 minus 2. So our velocity at 3 seconds is going to equal negative 1 times 1. Okay, so our velocity at 3 seconds is equal to negative 1, which again, we're not too worried about the actual value. We just know that the velocity is negative. So in this interval, your velocity is less than 0. And from 4 to infinity, our test value, let's say we pick t equals 5, again, completely random. If you want to pick a billion, you're more than welcome to, as long as it's in that interval. Okay, so our velocity at 5 seconds will equal 5 minus 4 times 5 minus 2. Okay, which means, make that equal sign a little bit clearer. 5 minus 4 is 1. 5 minus 2 is 3. So our velocity at 5 seconds is equal to 3, which means it is positive. So in this interval, our velocity is greater than 0. Okay, so we know that going from left to right, or where your velocity is greater than 0, on the intervals from 0 to 2, that's our velocity greater than 0, or from 4 to infinity. That little, it should be like a very curved U. Kind of your or symbol. And from right to left, that's when your velocity goes in the negative direction. Why did I circle that? I didn't mean to circle that. And that's from the interval from 2 to 4. I meant to just circle that, not hold that, but oh well. Okay, so that's the answer to C. All right, anyone still writing? All right. Okay, now for D, we want to sketch the the particle. Okay, so if you remember, our position function, P of t, is equal to t to the third power minus 9t squared plus 24t plus 4, where t is greater than or equal to 0. Okay, so we have to find the position when t is equal to 0, t is equal to 2, and t is equal to 4. So we're going to find the position where it all started, and we want to mark the positions where the particle is at rest. Okay, so we're doing this to sketch the graph. Okay, so first we're going to find P of 0. Oh, that's just 0 to the third power minus 9 times 0 squared plus 24 times 0 plus 4. Okay, so we know 0, 0, and 0, those all cancel out. So we're left with just the plus 4. So P of 0 is equal to 4. So this is our position at t equals 0. Our position at 2 seconds is equal to 2 to the third power minus 9 times 2 squared plus 24 times 2 plus 4. Okay, so P of 2 is equal to 24. And that's our position at t equals 2. And you don't have to write these if you don't want to. I just do them anyway. Position at t equals 2. And our P of 4 is going to equal 4 to the third power minus 9 times 4 squared plus 24 times 4 plus 4. Okay, so we know that position at 4 is equal to 20. That's our position at t equals 4. Okay, so that gives us everything we need to make our graph. Okay, so again, we make our number line from negative infinity to infinity. So negative infinity to infinity. And of course, we are starting at 0, so we don't need the rest of that, but we'll leave it up anyway. Okay, so to kind of limit how many marks we have to make, we'll count by 4 since all of those are multiples of 4. It's the only reason I'm really doing that. So we have 4, 8, 12, 16, 20, 24, 28. And we could stop there, but I'll put 32. I should have made that lower. Why do I not give myself enough room? That is a horrible habit. I'm so worried about putting everything on one page. I always forget to give myself enough room. So I'm just going to erase that and lower it. You don't have to rewrite anything. I just want to make sure it's not running into the equations or the functions up top. There we go. And that ought to be plenty of room. So from negative infinity to infinity, 0, 4, 8, 12, 16, 20, 24, 28. Actually, as long as we go up to 24, we're good since that's the highest value. Okay, so we know that when t is equal to 0, our position is at 4. So our position is right here at 4, and that's when t is equal to 0. Okay. When t is equal to 2, our position is at 24. So we're going to put it at 24. We're going to have it a little higher up than this one. And that's at t is equal to 2. And when t is equal to 4, our position is at 20. So again, I'm just going to have it a little higher up than the previous one and put it right over 20. And that's where t is equal to 4. Okay, so everything we did on the previous page helps us here because we know that our graph is going to go left to right on the interval from 0 to 2. So from t equals 0 to t equals 2, it's going to go left to right. And we have that as kind of our vertex. And then from the interval from t equals 2 to t equals 4, it's going to go right to left. So from right to left, t equals 2 to t equals 4. So we're going to go ahead and write it like that and kind of make that our vertex. Again, it goes left to right from t equals 4 to infinity. So it kind of goes like that and keeps on. And because this represents the velocity, we know it also can represent the direction. So we can draw little arrows to let us know the direction. You can draw whatever arrows you like. You can draw it like that, or you can just draw regular arrows. And that's the direction in this interval. And that's That's the direction in this interval. So all the previous steps kind of led us in the direction of making this graph. Okay. So any questions on that one? Yes.
How do you get those directions?
We actually did that just before you came in.
Oh, okay.
So yeah, if you look at the video,
Yeah,
you'll see all of that there. All right. Okay. So now we're going to do a few applied problems, kind of prediction problems. But first, if you remember, just kind of a quick review. Let's say we have our value x and some value x plus h. Let's say when you plug in x, you get some value f of x. So if you plug in 3, you'd get f of 3. And if you plugged in x plus h, you'd get some value f of x plus h. Plug in 9, you get f of 9. Okay. Now remember also the difference in the y values represent the amount of change. So in this case, the amount of change is equal to f of x plus h minus f of x. Okay, where we know x plus h is greater than x because it's going to the right. Okay. Now, we had just some graph written in there where those 2 points appeared on that graph. Then the line between those 2 points, remember that's your slope of the secant line. Just f of x plus h minus f of x all over x plus h minus x, which is just h. And we know the rate of change at some value a is our first derivative, which is the limit as h approaches 0, f of a plus h minus f of a all over h. Okay, so let's say that we know that the distance between x and x plus h is just getting smaller and smaller and smaller. It's almost infinitely smaller. That's like said finding the difference between 4 and 4.000, and you put in like 30,000 zeros and then a 1 at the end. That's a very small difference. Okay, so we know that if that h is almost infinitely small enough, because it can be infinitely small because you'll never reach infinity, but it can be almost infinite or approaching infinitely small. Then we know that our f prime of a is approximately equal to your f of a plus h minus f of a all over h. That h is already approaching 0 at an infinite distance, or almost infinite distance. So if we multiply both sides by h, you know that h times f prime of a is approximately equal to f of a plus h minus f of a. So if we add f of a to both sides, that means that we have f of a plus h is approximately equal to f of a plus h times f prime of a. We can use this formula to find future approximation, or approximate future values. To find the approximate value of f of a plus h when given position value f of a, h, and the derivative at that value a. All right, anyone still writing? Oh, Zip's still writing.
You're good.
All right. Mm-hmm. Here we go. Okay, so let's say, for example, that the population of a city is tripling every 5 years. So if the current population is 10,000, what will the population be 2 years from now? Okay. So we need a position function. So we'll let P of t represent the population. T years from now. Okay. So instead of writing 10,000, 20,000, 30,000, we'll just say P of t in thousands. Where instead of 10,000, we just write 10, and we'll know that represents 10,000. Okay. So they already gave us that the current population is 10,000. So if we started counting right this very minute at that current population, then that's when our t is equal to 0. That's when we're starting our observation. Current population is 10,000 people. That means we know that P of 0 is equal to 10,000 or just 10. Because remember, that represents 10,000. They also told us that the population triples in 5 years. That means in 5 years, it'll be triple what it is now. It's just 3 times the 10,000 that's already there. Just 30. So we know that P of 5 is equal to 30. Remember, that represents 30,000. Okay, so we have our P of 0 and our P of 5. Well, P of 0 and P of 5. We have to find our f prime, well, p prime of a in this case. Okay. So if you notice, we have f prime of a is approximately equal to f of a plus h minus f of a all over h. Well, we can apply that here, because that's just our p prime of a is equal to p of a plus h minus p of a all over h. Oh, should be approximately equal to. Now with that h, you want to remember that h is the same as saying a plus h minus a. You can rewrite this as p of a plus h minus p of a all over a plus h minus a. So that means our p prime of 0 is going to equal p of 0 plus 5, which is the difference between 0 and 5, minus p of a, which is minus p of 0, all divided by a plus h minus a, which is just a plus h, that's your 5 minus 0. Oops, straighten that up a little. Okay, so our population in 5 years, remember that's 30,000, which is represented by 30. That should be approximate. I keep forgetting the approximately. Minus the current population, which is 10,000. Make that a little neater. That was a little bit close together there. Here we go. All divided by 5. Okay, so that gives us 20 divided by 5. So we know that our p prime of 0 is equal to 4, or approximately equal to 4. So we want to find out the population after 2 years, or the approximate population. So we can actually use the fact that we know that p of a plus h is approximately equal to p of a plus p prime of a times h. And that comes from the amount of change. Oops, not the amount of change. Here we go. To find our approximate value, which still stems from the amount of change. We just kind of built onto it. Okay, so that means that p of 2 is approximately equal to your current population plus your rate of change at the current population times h. Okay, so the population after 2 years is approximately equal to the initial population, which is 10, plus the rate of change to your initial population, which is 4, times your H, which we have to calculate because they didn't give us H. Well, in a way they did. But in this case, it's just 0 and 2, which is 2. But in case you didn't have 0 and 2, you wanted to calculate that. That's our 0, and that's our 2. It's our A, and A plus H. Okay, remember your H is just A plus H minus A. Which is just 2 minus 0. So H is equal to 2. Okay, so we can use that to state that our approximate population after 2 years, is 10 plus 8, which is 18. Or 18,000. So after 2 years, the population should be approximately 18,000. Move this down a little bit so you can see the whole page. There we go. All right, any questions on that one? All right, anyone still writing? All right. Okay, so now we're going to look at the revenue function. Okay. And your revenue is just the number of items you sold times the price that you sold it for. Okay, so that means that the revenue is generated by the sale of X number of items at the price or at the number of dollars per unit at that price. P number of dollars per unit. And that is given by our revenue function R of X is equal to the number of items sold times the price of each item. Now the cost function, that's just how much it costs for the manufacturer to produce some unknown number of items. So we'll say X number of items. Okay, so your cost function.
You need to unlock your iPhone first.
Okay. What did I say that was close to that? Okay, now the cost function, we'll denote that by C of X. And that is the total cost to manufacture, let's say, X number of items. And our profit function, our profit is just equal to the revenue minus the cost. So that means our profit function we'll denote as P of X is equal to the revenue function minus the cost function. All right, anyone still writing? Okay. So let's say, for example, suppose the price demand and cost functions for the production of leaf blowers. Is given by, say, P of X is equal to 0.29x plus 13, and our cost function C of X is equal to 49x plus 34,535. Where we know that X is just the number of leaf blowers sold at the price. Number of leaf blowers sold at the price P, and that's in dollars. So we want to find the profit function. So first thing we have to do is find our revenue function, because they gave us the price function, but not the revenue function. And remember that your revenue or your revenue function is equal to X times P of X. Sometimes instead of P of X, they may just have P is equal to 0.29X plus 13, same thing. Sometimes they'll put the independent variable, sometimes they won't. That means your revenue function is equal to X times 0.29X plus 13. So if we distribute that X, that just means your revenue function is equal to 0.29X squared plus 13X. Which means we can find the profit function, which is P of X, by just having your revenue function minus your cost function. That means your profit function is equal to your revenue function, which is 0.29X squared plus 13X, minus your cost function, which is given to us up here, 49X plus 34,535. So to get rid of the parentheses, all we have to do is distribute that -1. So our P of X is equal to 0.29X squared plus 13X minus 49X minus 34,535. So just to simplify it, we can combine those two X terms, which means our profit function is equal to 0.29X squared minus 36X minus 34,535. Make that 3 a little bit neater. There we go. All right, anyone still writing? Okay. So that leads us into what are called marginal functions. Okay, so first be our marginal cost. And that's just the rate of change that it costs to manufacture X number of items. So how much does the price change at any given moment? That's the rate of change of the cost. To manufacture X number of items. See if I can get that markup out of there. There we go. And that marginal cost, you'll see that as M, C of X. That's just a notation for it. It's not M times C of X, which is C prime of X, the derivative of the cost function. Then you have the marginal revenue. And that's just the rate of change of the revenue from selling X number of whatever items you're selling at a particular price. That's the rate of change of the revenue selling X number of items at price P. The marginal revenue is just R prime of X. It's pretty similar for marginal profit. And that's the rate of change of the profit from selling X number of items at whatever price they were selling them at. And their marginal profit is just P prime of X. Anyone still writing? All right. Okay, so let's say, for example, that we have the cost function. In dollars. Of a company that manufactures vacuum cleaners. Is given by C of X is equal to 86 plus 15 divided by X plus X squared divided by 8. Where we know that X is the number of vacuums manufactured. Oops, straighten that up a little. So we want to find the marginal cost function. And straighten up that S a little bit. There we go. And instead of saying marginal cost function, they might even just say find MC of X. Same thing. Okay, so the marginal cost function is just the derivative of the cost function. So that's just the derivative of 86 plus, and instead of 15 divided by X, we're going to rewrite that to 15 times X to the negative 1 power, just so we can apply the power rule. Plus X squared divided by 8, we're just going to make that 1/8 X squared. Again, just to make it a little easier to deal with. Okay. Well, we know the derivative of a constant is 0. So that's just going to be 0. Let's straighten that up. And again, we're just applying the derivative to each term. Plus 15 times the derivative of X to the power of negative 1. Using the power rule, we bring down the negative 1. And we subtract 1. So that's negative 1 minus 1. Plus 1/8 times the derivative of X squared, which is 2X. Or you can say 2X to the power of 2 minus 1. Let me go ahead and write that. So our cost function would be, we can just eliminate that 0, no point even writing that down. So if we multiply those two factors, we get negative 15 times x to the power of negative 1 minus 1, which is negative 2. Plus, and we can go ahead and multiply those two. 2 times 1 over 8 is 2/8, which can be simplified to 1/4. That's 1/4 times x to the power of 2 minus 1, which is just to the first power. So that's your marginal cost function, or to get rid of that negative exponent, you say negative 15 over x squared. Just move it to the denominator and make it the exponent positive, plus x over 4. And again, with Newton, I don't think they accept it. They might not. Like I said, they kind of update every semester. So I don't know if they'll take the negative exponent or not. All right, any questions? All right, so we are done with 3.4. We're supposed to go right into 3.5, but unfortunately, when I was arranging my lecture notes, I allowed my cat to distract me, and I sat him down, and because he'll always start scratching the couch when he wants me to play with him. I was like, stop scratching that couch, and then I ran after him. And next thing I know, I grabbed my bag and put it up, left the notes right there. So we're going to start on 3.6, and then we're going to come in tomorrow and we'll probably get started on 3.6 today. We'll finish 3.6, and then we'll go back and finish 3.5 tomorrow. My notes should be sitting right on the table where I left them. So that was my cat bothering me story for the day. But that's my buddy, though. Right. I think I might need a little more paper. Oops. Here we go. All right. So section 3.6, cover the chain rule. Excuse me. Which is very, very, very useful. If you're taking Calc 2, Calc 3, and everything else, the chain rule is going to show up over and over and over. Okay, so what if we had y and we wrote it as a function of u? Or you can just write it as a composite function. So let's say y is equal to f of g of x. Okay. So we know that it is a differentiable function, which means the derivative exists across the interval. And we know that that internal function, g of x, is also differentiable, which means that its derivative exists. Then we know that y equals f of g of x is also differentiable, and the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. Or we can rewrite it as derivative of y with respect to x is equal to f prime of g of x times g prime of x. Make that prime a little clearer. There we go. Okay, now this one is the most commonly used when dealing with your everyday problems that require the chain rule. But you can use this one, but just in general, as far as like method of which one is easiest, this one you would use more with implicit differentiation. With implicit differentiation. And we cover that in section 3.8. Oops, bring that down a little bit. All right, so let's prove that the derivative of our compound function is actually equal to that. And this proof is pretty quick. We can probably do it on the lower half of this paper. So the chain rule at some value x is equal to c. Okay, so if we find the derivative of f of g of x, we can write that as the limit, instead of f of x plus h minus f of x all over h, we can just say f of g of x minus f of g of c divided by x minus c as x approaches c. So we can use the second limit definition of a derivative. Okay. Now with this one, we're going to have to kind of manipulate it a little bit. So we're going to multiply it by g of x minus g of c divided by g of x minus g of c. And draw a little arrow there. So that gives us the limit as x approaches c, f of g of x minus f of g of c divided by x minus c times g of x minus g of c, and didn't give it a whole lot of room. I'll draw a little box around that one. G of x minus g of c divided by g of x minus g of c. And we'll just enclose all of that. Okay, so if we go ahead and decide we're just going to exchange those two denominators. We're going to move this one over here and this one over here. And after we do that, we're going to distribute the limit to both of those. Because remember, multiplication is commutative, so you can just switch them up. So if we apply the limit to this first factor, that's the limit as x approaches c of f of g of x minus f of g of c divided by g of x minus g of c.